Hey, welcome back to AP Physics 1. Today we're going to be determining the speed of sound traveling through air. Well, we know what the equation for the speed of sound should be. It's V sound is given by 331 degrees plus 0.6 times the temperature. That's in Celsius, degrees Celsius. And this should tell us what the speed of sound is traveling through the air right now in this room. So I have a thermometer here, and the room temperature that I'm reading is about 3. So 22, 23, maybe 22.5 degrees C. So we have that. C is equal to 22.5 degrees in Celsius. So you can plug that in. We can determine the speed of sound. That is going to be our actual, or you could say theoretical value for the speed of sound. We're going to compare it to an experimental value that we can use to determine sound, and that is via tuning forks or producing standing waves using tuning forks through a chamber. The way we're going to do that is we're going to have a closed tube. We're going to produce a sound, and we're going to change the length of the tube until it produces the first standing wave. And for a closed tube, that's going to look something like that. So that will be the first standing wave that's generated inside the closed tube. How long is the wavelength? Well, if this is L, then we have L is equal to 1/4, because you need 4/4 of these to get one full wavelength. So we'll have 1/4 the wavelength, and therefore lambda is going to equal 4 times L. So there is lambda that we can use. The tuning fork, the sound that we're producing that's going to be generated by the tuning fork, is going to be given. So we don't have to calculate that. So here are specific tuning forks. You hit them, they create specific frequencies that will resonate when you put it through the tube. Okay? So one other thing that I'll mention, and I guess I'll write this down, frequency is going to be given to us, is that there's a little bit of error that is associated with an open tube that we have to consider. So instead of using this equation right here to determine lambda, we're gonna adjust it a little bit. We're gonna add a correction factor to it. And so instead of using this as our wavelength, what we're gonna use instead is lambda equaling 4 times L, just like before. Oops, I'll write it as lowercase l. But we're going to add a correction factor, which is going to be 0.33 times capital D. So our actual wavelength with the correction will be 0.33. You could try 0.3 or 0.4. Sometimes I see it in like different notes that it's 0.4, sometimes it's 0.3, so I just put something in between, 0.33. And D is the diameter of the column that we'll be measuring, and I already measured that for you. D, the diameter of the column, is going to be equal to 0.027 meters. Okay, so that's D. This is how we find the wavelength. If we know the wavelength and we know the frequency, we can use the equation. Velocity for any wave is given by the frequency times the wavelength. We're going to be using multiple frequencies here, so it's not good enough to write this equation out. You're going to have to make a table here. So multiple frequencies, and then you'll get the length from here. And then when you have the length, you can find the wavelength lambda. Once you have this and this, you're going to plot a graph. I'm not going to tell you what it is. You have to plot the graph yourself. Put something here, put something here. You'll get a line, and the slope of that line should give you velocity. So we did a worksheet about something similar to this, so you shouldn't have too much trouble figuring out what goes here and here. But the ultimate goal is the slope of this line right here should give us velocity. Once you have velocity, you can compare it to the theoretical value or the actual value for the speed of sound and see how close you got doing this experiment. Okay, so the last thing to do is just to actually do the experiment. So here's the experiment. We've got our resonance column right here. We've got different tuning forks with different frequencies. I'm going to adjust this resonance column. The other end is filled with water. As I rise this, some of the water is going to decrease down, but I've already accounted for that. I've actually put a little scale right there. So that should be okay. As soon as I hit the tuning fork and I start to adjust this column right here, eventually you're going to hear that resonance sound. That's the first standing wave being produced. That will give you 1/4 the wavelength. So you're going to use the adjusted wavelength equation that I mentioned before once I've given you what L is. So then you'll get the wavelength, the frequency I'll tell you as well. You're going to take those values and then make a graph, and then using that graph solve for the speed of sound. Okay, so the first frequency that we're going to be using is 256 hertz. It's going to be a 256 hertz tuning fork. I'm going to give it a strike and then I'll measure what L is going to be. So let's do that. We'll move it. About right there. So let's do it again. Right there. And so at 256 hertz, I'm going to get L is equal to 0.34 meters. So L is going to be 0.34 meters at 256 hertz. Let's go on to the next frequency, which is a 320 hertz tuning fork. I'll give it a strike. So that was 0.26 meters. L was equal to 0.26 meters at 320 hertz. Let's put this down, move on to the next tuning fork, give it a strike. Okay, so at 384 hertz, L is equal to 0.22 meters. At 384 hertz, the length that I measured was 0.22 meters. Let me just make sure of that. Yes, so L is equal to 0.22 meters. And then the last tuning fork is going to be a 512 hertz tuning fork. So let's give that a strike. Okay. So that was L equals 0.16 meters. At 512 hertz, the length was 512 hertz. So those are our 4 points. That I only got 4 tuning forks. So we're going to have 4 points, graph it, find the velocity of sound that way. The actual value, we were going to use 22.5 degrees Celsius. So using the actual value equation, you'll find the speed that way. And now hopefully you'll be able to find the speed using the experimental calculations and then just compare the two. So that's how you do the speed of sound. I'll see you in the next lab. Adios.